Okay, let's see what happens to our PN junction when we bias it with the forward bias, meaning that we connect the battery to the PN junction, where the positive terminal of the battery is connected to the P-type and the negative terminal is connected to the N-type. So what happens is that this positive terminal here, this positive voltage here, is going to push more and more holes into the P-type material, and these holes are going to go in and recombine with the ions, the negative ions, and kind of like basically cancel out the ions and or neutralize the ions. Similarly, we're going to have electrons moving in here and neutralize the positive ions on the left side. What is the outcome of this? Well, the electric field that we had here, due to this depletion region, becomes smaller and smaller. Why? Because, well, the depletion region is becoming narrower and narrower. So the more voltage I apply here, the smaller the depletion region, or the narrower the depletion region gets. And at some point, I'm not going to have any depletion region. I'm just going to have so many holes coming this way, coming into the P side of my PN junction, and so many electrons coming to the N side of my PN junction that there's no way for the ions to actually be generated. So the moment they get generated, they're going to be canceled out or neutralized by these extra holes that are coming. So I'm going to have the free flow of excess holes from right to left and excess electrons from left to right. Therefore, I'm going to have a huge amount of current going from right to left as the overall, or as the combined effect of the two carrier movements. Okay, two types of carrier movements. Now, how do I quantize this current? So now I know that when I have a V forward bias with this kind of polarity, I'm going to have some current. Let's call this I. And since this is a diode, let's call it the ID, right? So now the question is that if I want to plot this ID versus VD, so if this is ID and this is VD, how's it going to look like? I know that I'm going to have more and more current when I have more and more voltages, but then is it going to go up linearly or exponentially or quadratically? Well, it turns out, again, the proof of this equation is in your textbook. It's the outside of the scope of what I want to talk about in this course, because we want to actually get into the circuits as soon as possible. So I'm not going to actually talk about the proof. It's actually quite simple, but it's pretty long. So if you want, you can actually look at the textbook and find the proof. It turns out the current, the equation that is governing the current, is an exponential equation. So this exponential expression is something like this. So we have an IS, which we call it the reverse saturation current. I'm going to tell you why we name it this in a moment. And then e to the power of Vf over Vt, Vf being the forward voltage that we have applied, the voltage of our voltage source. So this is our Vf. And Vt, if you remember, we have defined it from in the past that Vt is our terminal voltage. It's equal to 26 millivolts. It's our kT over Q, right? So this is a constant. The Vt is constant, at least at the room temperature, and Vf is the only variable on the right side of the equation. So now we have an equation that is basically telling us how the current of our diode is actually changing with the voltage across the diode, if it is a forward bias, meaning that the voltage polarity is in this way, right? The positive terminal connected to the P side. So this point of my plot is the equilibrium, right? No voltage has been applied to my PN junction. The more positive voltage I apply, let's call this VD, or we can call it VF as well, the more current I'm going to have, and this current is actually going up exponentially, right? Meaning that after a certain point, it's almost kind of like fully vertical, right? It is very interesting to know that this equation is actually valid when we make the voltage negative, the forward voltage Vf a negative voltage. What does it mean when it's negative? It means that it's a reverse bias. It's not a forward bias, right? So VF here being negative, it's like if I have a negative 2 volts here, it's as if I have a 2 volts with this polarity, right? We know this from electrical circuits. So when I have a negative voltage here, if you look at the math, you see that I'm going to have a negative number here, or basically, a negative number here, and e to the power of a negative number is going to get closer and closer and closer to 0. When VF is negative enough, it's just going to be, the entire thing is going to be 0. But then one thing I know is that when VF becomes negative, the moment it becomes negative, e to the power of a negative number is less than 1. Therefore, something less than 1 minus 1 is going to give me this entire bracket is going to be a negative number. So my current is going to be some negative number times IS, right? So I'm going to have a little bit of a negative number, and then the more negative VF becomes, the more the closer this term becomes to 0, right? And it quickly actually gets to 0. Like imagine that this VT is actually 26 millivolts. So if I apply only 100 millivolts, I'm going to have e to the power of 100 over 26. Let's say it's 25. So it's going to be, negative 100 over 26. So negative 100 over 26 is around negative 4. E to the power of negative 4 is very close to 0. Even with negative 100 millivolts, I'm almost at 0, right? Imagine that if I apply negative 1 volt or negative 2 volts, right? So very soon, this entire bracket, let me actually erase all this stuff. This entire bracket here is going to be just approximately negative 1 because the exponential term becomes approximately 0. So very soon this thing saturates to a level that is equal to negative IS. So this is the reason that we call IS the reverse saturation current, meaning that if you apply a voltage with a reverse bias in this direction, ideally you don't have any current, but then for any diode, depending on many different parameters, you're going to have a little bit of a current. And by a little bit, I'm talking about femtoamps and picoamps, right? So it's something that we can always think that it doesn't exist. That's why we even called the reverse bias diode a capacitor, because we know that there's no current passing through a capacitor, right? But it is a very small amount of current, and it is in the reverse direction of a normal, in the reverse direction of the normal diode current, right? So normally the diode current is always from the P side to the N side, but then since this current is actually from the N side to the P side, we call it the reverse current. And since it saturates very quickly, it's almost always in the saturation it has the saturation value, we call it reverse saturation current, or IS. Okay. Now you might think that, well, the current of this PN junction should be a function of other things as well. For example, how big is my crystal, or what type of a semiconductor do I have? Is it basically is it a silicon semiconductor? Is it germanium? And then what is the doping level of the N type and P type? Is it the 10 to the power of 15, 16, 17? All of those things actually do have and do play a role in calculating this current, and all of them are actually embedded into this IS. So if we want to write the IS, this is the equation that is governing the IS. So the saturation current is A Q Ni squared times this bracket. So what are these things? A is the cross section of my crystal. So if this is my PN junction, this is the cross section of the crystal, and you can imagine that the wider is this cross section area, or the bigger is the cross section area, the more current I'm going to have, or the more leakage I'm going to have, right? Q is the charge of an electron. Ni squared, Ni, we know what it is. It's the carrier density of an intrinsic semiconductor. So if this is silicon, this is 10 to the power of 10. If it's germanium, it's going to be some other number. So that's how different material is going to affect the current. We know dN and dP. These are diffusivity of electrons and holes. And we know Na and Nd. These are the doping level or doping concentration of the acceptor atoms and the donor atoms, the borons and the phosphorus, for example. The Ln and Lp, these are actually called the diffusion length. Again, it's something that is outside of the scope of our discussion, but just for you to know, it's basically the average distance that a free carrier or an excess carrier covers until it recombines. So like if you have a hole on the p side and it actually goes to the n side due to the diffusion, after a while it's going to recombine with some sort of an ion there or some atom that requires a hole, right? So the average distance for these free carriers, we're going to call it the diffusion length, and for holes we're going to call it the Lp, and for electrons we're going to call it Ln. Okay. Now our discussion of diodes is almost complete. So now that we know how the diode works and we know the current voltage relationship of a diode, we can appreciate more why the diode symbol looks like this. So this is the p side, this is the n side. The p side we call it, as I mentioned, cathode, and the n side we call it the anode. And we can see that why the symbol has kind of like a directional implication basically built into it, and it's because of the fact that the diode allows for current to flow in this direction if we apply a good amount of voltage. So if we apply a voltage with a forward bias, so if we have this V forward, we're going to have some current. But then if I flip the polarity of the voltage source here, the battery that I've connected here, and make this diode biased in the reverse condition, then I'm not going to have any current. So this symbol is trying to imply that, right? So in one direction I have current, and in the other direction I don't. And the current, it has an exponential equation. So one last thing is that, again, looking at this equation from the mathematical point of view, we can see that if Vf becomes much greater than Vt, then you can comfortably say that e to the power of Vf over Vt is much greater than 1. Therefore, I can kind of ignore the 1, right? So the rule of thumb is when Vf is equal or greater than 4 Vt, we can typically say that ID is approximately equal to Is e to the power of Vf over Vt. So we're going to ignore the negative 1. Okay? So both this equation, but then you can see that when we do the approximation, then the equation is not really valid for the reverse condition or the reverse bias condition. It's only valid for the forward bias, but both this equation and the main equation are going to be very useful for us in analyzing diode circuits and diode-based kind of electronics. Okay? Okay, before wrapping up this lecture, let's solve an example. So the example is telling us that if Is is 10 to the power of negative 16 amperes, and we measure a forward bias current of 1 milliamp, what voltage is applied to the diode? So basically, at this time, the current is actually given to us, and we are trying to find the forward bias voltage, or Vf, right? So from previous slide, we know that ID is equal to Is e to the power of Vf over Vt minus 1. Now, since we know that the current is actually 1 milliamp, which is a decent amount of current, I can imagine that this Vf is probably much bigger than Vt. So I'm going to assume that I can make the approximation, and in the end I'm going to check my answer and then see if my assumption was correct. So I'm going to say that ID is approximately Is e to the power of Vf over Vt. So I'm going to forget about negative 1. So from there I can say that ID over Is is equal to e to the power of Vf over Vt. And from there I can say that Vt times ln of ID over Is is equal to Vf. So I found an equation that is basically based on Vf. So I have ID, it's given to me. It's 1 milliamp. And IS is also given to me, 10 to the negative 16 amp, so 1 milliamp or 10 to the negative 3 amperes. And I know how to take the ln, and I know VT is equal to 26 millivolts. Okay, so I can actually calculate this VF. If you do the math, you're going to find VF to be equal to 778 millivolts. Okay. The second part of the example is asking us how much should the voltage increase to raise the current by a factor of 10. Okay, so I want to have a current of, well, I had it at 1 milliamp, now I want to have a current of 10 milliamp. And the question is asking me what should be the new VF. Okay, well, I'm going to say if VF1 from the equation that I found is equal to VT ln of I1 over IS, and VF2 is equal to VT ln of I2 over IS, I can safely say that VF1 minus VF2, because that's what the question is asking me, how much the voltage should be increased, right? Sorry, VF2 minus VF1 is equal to VT ln of I2 over I1, because the IS's cancel. Okay, so I know I2 over I1 is 10 and VT is 26 millivolts. So this is going to be 26 times 10 to the negative 3 times ln of 10. Again, if you do the math, you're going to find something like 60 millivolts. This means that I need to have a VF. So VF2 is going to be 778 plus 60 millivolts. So 780 plus 67 is 840. So this is going to be 838 millivolts. Okay. Now, what's the lesson that we can actually learn from this? So it's actually the third bullet item up here. So it's asking us if the currents that we use in electronics are in the order of milliamps to tens of milliamps, what does this mean for our diode voltage? So basically what it's telling us is that in electronic circuits, especially integrated circuits, especially inside the microchips, we don't have currents that are in the order of amps or even like hundreds of milliamps because, well, things will burn out. Remember, like the size of these chips are in the order of like nanometers and micrometers. So you can think about it if you have a conductor with a width of a few, like 1 or 2 micrometers, and you have a huge amount of current, and by huge I mean hundreds of milliamps flowing through it, that conductor is going to just burn, right? It's going to get heated up and it's just going to damage everything, right? So generally with microelectronics, we are really talking about at most milliamps and tens of milliamps. We're not going to talk about anything higher than that. Generally low power electronics with, like, for example, implantable devices and things like that, we're really talking about microamps, and in some certain blocks, we're really talking about nanoamps and picoamps and even femtoamps, right? So here we're talking about like milliamps. So if the maximum current that we're going to have in a diode is the order of tens of milliamps, what does it mean for the diode voltage? It means that, well, we're not going to have a diode voltage that is in the order of a volt or higher than a volt. Why? Because if 1 milliamp resulted in 778 millivolts, and 10 milliamp resulted in 838 millivolts, it means that every 60 millivolts, I'm going to, well, multiply this current by 10. So for 100 milliamp, I'm going to get somewhere around 900 millivolts. Remember, the current voltage relationship is exponential, right? So after a certain point, it gets pretty vertical. So like by changing the voltage a little bit, you're actually, by changing, and you can see it here numerically, by changing the voltage by only 60 millivolts, I'm multiplying my current by a factor of 10. So you can imagine that if you actually go to a diode voltage of 1 volt or 1.1 volts, we're really talking about amperes, a few amperes or even more than that. So this is a nice sanity check for you guys, that if you're actually doing any kind of diode circuit analysis and you find the voltage across the diode to be anywhere around, like anywhere more than 700-800 millivolts, you have to double check your equations, your calculations, and then If you found anything higher than like 800, I don't know, 50 millivolts, I promise you something is wrong, right? There's definitely something wrong in your calculation. You have to actually go and find it.